We are Team 4. We're going to be presenting our gearbox design. I'm Jonathan Vega. This is Trevor Solórzano, and this is James Taylor. A gearbox is a collection of gears, shafts, and bearings all put together in order to be able to reduce or accelerate the speed or output of the shaft. All the parts surrounded by an outer casing will be filled with oil to protect them, as well as from outside contaminants to extend the life of these parts. We will also have input and output shafts, and the angle between both these shafts will vary, depending on the application. The two types of gears we'll be using will be bevel gears and spur gears. We will be having many shafts inside this gearbox. The ball bearings will be used for our bearings, and the gearbox casing will, of course, be surrounding our entire system. Now, some applications for the gearboxes are very diverse in the engineering fields. We have them in agriculture, aerospace, automotive. This gearbox in particular will be used for a conveyor belt, and we did highlight one very good gearbox, the Dynaboot XL series, which is specifically tailored to high torque systems. So what to consider, we have to take into account the gear ratios, the horsepower to transmit through the system, the desired output torque and speed, as well as the gear arrangement needed in order to make sure that we do achieve this, and of course backlash, vibration, the environment and structural supports that could affect the gearbox itself.
Okay, so our specific gearbox, we needed to meet certain specs. So we needed to be able to transmit 3.5 horsepower. We needed also to do a 15-to-1 speed reduction. Our input speed was 1800 RPM. It needed to end up being 120 RPM. So also we had to make a perpendicular output shaft, and we also had to make it spin in the opposite direction. So our design method, the things we used to basically pick our gears was based on the Boston gear. The catalog had many gears inside of it. We had to make sure the horsepower ratings were up to spec so that they would be able to transmit the 3.5. So the gears were also run through AGMA stress analysis for bending and contact wear. We were also able to make a housing for the entire gearbox, and we were able to fit everything inside as compact as we possibly could. So the types of gears that we use here is like a picture of it on the left side, on the right side. We have a 3-to-1 gear reduction with bevels. This is what made the 90-degree output that we needed. We have a spur gear, which is a 2-to-1 reduction to an idle gear, which then goes to a 2.5-to-1 reduction. That makes our 15-to-1 reduction total. We have the last spur gear, which is actually cast iron. Just that's the only material that was different from the rest of the gears, and that's it's a pretty good example of what we did. Now for the bearings, we just basically had to choose bearings that were able to carry the load of the shafts. We were able to do force analysis on all the shafts, and then these are the bearings that we chose. We also rated them against 4,000 hours per year. When we did factor safety on that, we were able to see that the factor safety were very, very good. So the bearings that we chose definitely went above and beyond what we needed.
Okay, so for the gears in our system, we decided to go with 2 bevel gears and 3 spur gears. Each of them for the bevels had 20 and 60 teeth respectively, and for our spur gears we had 12, 24, and 60 teeth respectively. So our shafts used were based upon our bore diameters for each particular gear. We had 875 inches, 0.75 inches, 0.875, and 1 inch, and gears 2 and 3 had to share the same shaft, and you can see listed here for the factor of safety for torsional stresses. Each of our factors of safety were greatly above 1, so they will last a long time without failing. Now for our bending and wear for gears, we have the factors of safety for our bending stresses and for our wear stresses. Again, for each particular gear, our factors of safety are greater than 1, meaning that they will not fail in the conditions that we set them for. So our cost analysis, based upon looking at our catalog, we decided to go ahead and do some research on which ones would be the cheapest particular gears or bearings for our particular application, and we came up with a total gear cost, or a total final cost of $452.33. On the left here, you can see our simulation of our system, completely finished with a gearbox outer casing made of steel. On the right here, we have a conveyor belt used for mining applications that also will produce 3.5 horsepower needed to suffice for the job. And here is the actual simulation, the actual motion simulation of our system. In conclusion, many trials were done to pick the correct gears, shafts, and bearings. We ultimately succeeded in creating a perpendicular shaft and lowering our speed from 1800 RPM to 120 RPM and delivering 3.5 horsepower.